very happy to be here. Thanks for the opportunity. This talk is really about how one of our close partners and customers, SoftBank, is using our technology to solve problems that are very real world. But before I transfer the mic over to Yamauchi-san, I'd like to say a few words about some of the work that we have done recently. Many of you might have attended Mike Biersak, our CEO, who's sitting in the audience, his presentation, and we might otherwise be very well known to you, but yeah, we'll take this as an opportunity to maybe refresh your knowledge about Q-Control. What we do is build AI-powered error suppression software, and we fall under the category of infrastructure software. And what we do is make quantum hardware useful. And our almost pioneering contribution to this sector is the introduction of some key layers in the quantum computing stack above the physical qubit hardware. This includes the quantum firmware, compilation, error correction methods. And the reason we did all that was to solve one problem that afflicts the whole quantum computing industry, and that is that there are hardware errors that impede meaningful demonstrations to be conducted on real-world quantum computers. And this is almost holding back the whole quantum computing sector. Right? This is one reason why people have been skeptical about how long it'll take, etc. So, and I'm not going to dwell into this too much, but as you all know, there is a lot of noise in quantum computers, and the question is, how do we remove that noise? The way in which our software works, and this is specifically called error suppression, is through a set of steps. Right, and those of you who have looked into the problem know that taking out all of the error requires a whole number of steps that have to be linearly executed. But it's a very, very difficult problem. As some of you might have heard, Mike, when he came out of Harvard, there were maybe 12 people specialized in this whole area. And if you look at the whole pipeline, starting from input code through compilation all the way through to results, any one step, even compilation, can itself be a lifetime of research, right? And this is what researchers like to do. They really try to understand the problem. They like to benchmark different alternatives, etc. But decades of work has been put into the products that we have and the technology that we have, and our team is really the world's foremost team of quantum control experts, and we put a lot of effort to package all these solutions. But before I get into our solution, let's actually walk through some of the challenges. Right, compilation. There's a lot of installation, configuration. Similarly, mapping your circuit to the actual hardware, to the pulse design, where there's a lot of manual work involved. To the work on the actual computer, where your code will need to get executed, and once you have the results, you have to perform something called as measurement error mitigation, because your actual solution will have additions of noise that come from various sources. Let us say you're able to take each one of these steps and maybe even get optimal solutions. What's going to happen is that when you put it all together, you'll find out that there will be incompatibilities between the various steps. And in total, you will have a lot of overhead. This is why this is a very, very difficult problem. And this is not simple post-processing. This is not, okay, I'm going to run a problem on a quantum computer and post-process the results. Because this whole pipeline, the reason we are doing all of this is so you can avoid the noise in the first place and make your system resilient to the noise as much as possible, and in doing so, achieve the maximum possible performance from your quantum computer. And what we did was, this is our contribution to the whole industry. We put the whole stack together. We used all of the knowledge that we have, and it took years of perfection. And yeah, now we have a fully integrated pipeline that we are, by the way, constantly improving. And we created this completely autonomous AI-driven toolchain that suppresses errors, right? Not mitigates errors, suppresses errors. And so your quantum computer is running at its absolute maximum possible performance, only limited by hardware, without extra overhead, right? And we call this product that runs on the cloud as FireOpal. The way in which these methods work is published in the literature, where we talk about the physics involved in each of these components. And how do we know it works? Our results speak for themselves. And we have various publications out there, but the typical results that you obtain with the software that we have gives you the ability to run much deeper circuits. Why do deeper circuits matter? If you're, for example, if you're in the financial services industry, you want to run very deep circuits. The number of shot counts that you require typically to get the right answer is drastically reduced. And why do shot counts matter? Because quantum computing access time is fairly expensive. And you want to, as researchers, you want to get your results in as quick a time as possible. And finally, the performance gains that we deliver are typically, in several orders of magnitude. And I have references to the published literature as well. So, talking about the previous Grover search problem that I had shown, where the default, system performance is noisy. Q-control software transforms that, and you get the right answer typically within the first few attempts. So with minimal overhead on the system, which results in more efficient execution. And here is an example of how we are driving innovations in this industry and solving some very, very fundamental problems. As you very well know, combinatorial optimization problems, binary optimization problems are ideally suited for quantum computers. Until now, it's been typically like quadratic optimization type problems, but now we have gone beyond, right? We took a 127-qubit Ising spin glass problem, where you have to find the ground state energy and find it as quickly as possible and find it as as accurately as possible. And the kind of problem that I describe is amongst the largest optimization problems that have ever been run on a gate-based quantum computer. And the results are transformational, right? We easily beat what you can typically get with a best-in-class local solver, which typically uses like a greedy optimization to looking at a random distribution of candidate solutions. And what we achieve is very, very close, or at least we get as close to the real answer. The red vertical line that you see is the ground truth, and this is a maximally optimized C-plex solver. We're not claiming quantum advantage here, but we get as close to the ground truth as possible. And the best result that you can ever get with annealing solution is shown in this green bar, right? And that's the best in class, right? And previously, it had been thought that annealing machines tend to be the best on optimization type problems, but we with this example, we just beat the annealer by 1500x. So yeah, I mean, this is just one example of the type of result that we have gotten with our error suppression pipeline. I'm going to pass it on to Hiroshi-san, our partner at SoftBank, and let him talk about how he used our pipeline to solve a different type of problem, a quantum kernel problem. So here's son.
Thank you. I am Yamauchi from SoftBank, and at our leading edge laboratory, beyond 5G is what we are studying together with digital twin and multimedia technology and quantum technologies. And this time, IBM quantum computer Kawasaki went into operation last year. And by using certain use cases, demonstration using quantum computer was what we aimed to conduct, and automation of network operation was identified as the area where we use kernel. And Professor Sogabe and Professor Lot from Keio University, and we conducted the three-party research. This paper itself was uploaded onto the archive last month, but in September, the Quantum Week also adopted this paper. Firstly, here is explanation on problem setting as the network configuration. As you see, here is the nationwide network configuration. So access, fixed network, and from area to core, and from IX to internet. So this is the structure. So basically, this is the configuration of corporate network. Smart VPN, smart internet are the services for corporate clients, which are being delivered. And here is the troubleshooting workflow. We are monitoring individual services, but clients sometimes let us know of issues they are facing, and we conduct troubleshooting of networking with our network engineering team 24 hours a day. In some cases, operators or engineers are dispatched to the client site to replace some components or implement some workaround to restore the system. The use case using quantum computer this time uses this system. So this kind of system behavior, well, service path is identified from database, and each device's IP address is identified, and we log in there, and through commands, the areas to address is identified, but the network itself is growing bigger and bigger. So from manual work, we are switching to the automation using system. That's what we have been promoting. And recently, automation through machine learning by AI is something we've been promoting recently. And the data set from the system log, the data set has been extracted. And just like NIST, on the horizontally, there are different types of command, and vertically, well, again, these plots show the abnormalities that comes out from the command exercised. And if there is no abnormality, you see the blank. So abnormal patterns are seen as the feature vector horizontally, and vertically you see the failure patterns. So there are 7 types of failure types, as you see on bottom right. So based upon these failure types, data set is created. In setting problem, data set is learned by the system, and the abnormality patterns, what kind of the classes of abnormality patterns are estimated. So that's the approach. And this is the system deployment, and this is the workflow in the case of system deployment. So this is offline learning flow shown by the solid line, and using the learned model, the dotted line or online, the class estimation is done. So with classical computers, well, and quantum computers, the calculations are done, performed by classical side is this side, and quantum calculation side is this side. Kernel is used, and 120 dimension, but as we perform the experiment, the dimensions are reduced to 50. And the training data is divided and parameterized, and parameterized circuit is created. And the internal product calculation is done by quantum computer, and ground matrix is all patterns of feature vectors are taken to calculate the inner product, and the resultant kernel is this ground matrix. And proposed and conventional settings are shown. The conventional XL and XM, the two vectors that have inner products, to these two vectors, XL is parameterized, and the other circuit is added, and the result is measured. So this is what's called conventional. So internal inner product calculation measures the probabilistic distribution. Conventional just performs a simple calculation for the proposed. The adjacent qubits, the phase difference is adjusted by Rz. So strength of entanglement for the adjacent parameterized XP and Q, the alpha coefficient is adjusted, and the estimation or approximation accuracy is adjusted. So entanglement effect through our approach is validated. That's what we have been doing. So tensor network up to 50 qubits, the features are evaluated, and the result is this. The proposed orange line is proposed, and the blue is conventional. Classical SVM is used for the green, and the proposed result on average is outperforming. So it's 100 times. Test data, training data are divided, and that's done 100 times. Then the results are evaluated, and proposed outperformed. Sometimes we see the classical having been outperformed, but we are seeing the changes in accuracy. So 0.6 is where we attain the peak. As you see here, the alpha parameter entanglement strength is adjusted to calculate the kernel. Then, depending on the types of data set, certain optimum value is derived. So the data set, it depends on the characteristics of data set, but number of qubit, what is the scale of a qubit for calculation, and how do we adjust alpha parameter. So depending on those things, we could address to a certain degree of data sets. So up to this, I've explained the simulation result. And next, IBM Kawasaki was used for performing experiment. But in the first place, classical SVM, 85 to 89% was obtained for the data set which we used for calculating kernel. And simulation is considered as the ideal. So blue is a state vector simulator that can calculate only up to 30 qubit. And orange is the tensor network calculated result. So tensor network has some variance, but green is IBM original error mitigation M3 and optimization level 3. So to a certain extent, on the side of IBM, they did well, and the result is green. And red bar is the estimation accuracy. And at the 30 qubit point, 82% was the value attained. If IBM is used, the ratio is 50%. So by using Q-CTRL, so this much of gain was obtained. As a result, 80% of accuracy was obtained with the real machine. That's what we've confirmed, and it's a practical result that we could confirm. And this side, at the 30 qubit level, 784 point inner product calculation was made. So ideal simulation, this is custom data. So relative differential is shown by this distribution, but the IBM green points, based upon the result of inner product, the Q-CTRL is used overall. This level of the accuracy was obtained. So Q-CTRL's accuracy or performance in this experiment was shown and seen to have contributed in boosting accuracy. So that's the result of the experiment we've conducted. Thank you.